A crumpled ball of aluminum foil sits in a mug of warm salt water on a kitchen counter right now. 30 seconds ago, the water was 72 degrees. Now the thermometer reads 82. No flame, no plug, no battery, no fuel canister with a barcode and a price tag. Just two materials that cost a combined 11 cents, pulled from the same drawer where you keep the rubber bands and the takeout menus. The foil is dissolving, hydrogen bubbles are climbing the surface, and the water is getting hotter by the second. A single gram of aluminum releases approximately 15 kilojoules of thermal energy when it reacts with water. That is real, measurable, published heat from a material you throw away after wrapping last night's leftovers. And 23 states have now written laws that make it functionally illegal for you to use this reaction to warm anything in your own home. That should tell you everything you need to know about who this threatens and why. Aluminum was not always disposable. In 1852, a single ounce cost more than silver. Napoleon III reportedly served his most honored dinner guests on aluminum plates, while lesser guests ate from gold. The metal was rarer than platinum in refined form, locked inside bauxite ore by bonds so strong that no furnace on Earth could break them affordably. Jewelers mounted it in brooches. Scientists displayed it in glass cases. A kilogram of pure aluminum in 1855 sold for roughly $500 in today's money. Then in 1886, two men working independently on opposite sides of the Atlantic, Charles Martin Hall in Ohio and Paul Héroult in France, discovered the same electrolytic process within months of each other. Pass enough current through dissolved alumina and pure aluminum drops out of solution like rain. The price collapsed. By 1890, a kilogram cost 30 cents. By 1910, Reynolds Metals was rolling it into sheets a thousandth of an inch thick and selling it to housewives for wrapping sandwiches. The most expensive metal of the 19th century became the most disposable material of the 20th. But here's the part that got buried in that transformation. The energy it took to rip aluminum from its ore did not vanish when the foil hit the kitchen drawer. It stayed locked inside every sheet, every crumple, every ball you had ever tossed in the trash. Aluminum is one of the most thermodynamically energetic metals on the periodic table. Pound for pound, it stores more chemical energy than most solid fuels. The only reason it sits quietly in your cabinet instead of reacting with the moisture in the air is a lock so thin you cannot see it, feel it, or measure it without an electron microscope. The moment aluminum touches oxygen, and that happens within milliseconds of leaving the rolling mill, a skin of aluminum oxide forms on the surface, Al2O3. This layer is between 3 and 5 nanometers thick, that is roughly 15 atoms deep, thinner than a single wavelength of visible light. You cannot scratch it off with your fingernail because it reforms faster than you can damage it. Scrape it and it heals in microseconds. Submerge it in water and it holds. Wrap it around acidic food and it barely flinches. This invisible film is the reason aluminum foil can sit in a humid kitchen for years without corroding. It is the reason a ball of foil dropped in a glass of tap water just sits there doing nothing. The raw metal underneath is desperate to react. It wants to oxidize. It wants to release its energy, but the oxide skin says no. Every surface is sealed. Every atom is locked behind a gate that almost nothing in your household can open. Almost nothing. Salt opens it. You have seen this your entire life without knowing what you were looking at. That corroded spot on the aluminum window frame near the coast, the pitting on a boat trailer that spent one winter near salt-treated roads, the way a cheap aluminum pan develops rough white patches after you boil salted pasta water in it one too many times. That is not random decay, that is chloride ions doing exactly what they do. Sodium chloride dissolves in water and floods the surface with chloride ions. These ions are small, aggressive, and relentless. They penetrate the oxide film at its weakest points, worming into microscopic defects and grain boundaries. Once a chloride ion breaks through, it exposes raw aluminum directly to water. And the reaction that follows is immediate, exothermic, and impossible to patent. 2Al plus 6H2O yields 2AlOH3 plus 3H2. Aluminum reacts with water to produce aluminum hydroxide and hydrogen gas. The hydrogen bubbles up visibly. The aluminum hydroxide precipitates as a white powder, and the reaction releases heat, significant heat. A 2-inch square of crumpled foil and a tablespoon of salt dissolved in warm water can push the liquid temperature up to 10 degrees Celsius under 30 seconds. Scale that up to a fist-sized ball of foil and a quart jar of saturated salt water, and you get enough sustained warmth to keep your hands from going numb in a freezing car. A single gram of aluminum liberates approximately 15 kilojoules. A standard roll of Reynolds wrap contains roughly 200 grams of aluminum. That's 3,000 kilojoules of thermal energy sitting in your kitchen right now. Enough to raise the temperature of 7 liters of water from freezing to boiling, from a $3 roll of foil and a container of salt that costs $1. Here's exactly what you need and what it costs. One standard 75 square foot roll of aluminum foil, $3 at any grocery store. One container of table salt, 26 ounces, $1. A glass jar or metal container that can handle heat. Warm water. Total cost, $4. That's it. Tear the foil into strips or crumple it loosely to maximize surface area. Dissolve 3 to 4 tablespoons of salt per cup of warm water. Drop the foil in. The reaction begins within seconds. You'll see bubbles forming on the foil surface almost immediately. The water temperature climbs steadily. The foil slowly dissolves over the course of 25 to 45 minutes, depending on the salt concentration, water temperature, and how much surface area you exposed. I tested this in my garage last January during a power outage that lasted 14 hours. The temperature outside was 19 degrees. Inside the garage, it was 38 and dropping. I crumpled half a roll of foil into a large mason jar, dissolved a quarter cup of salt in warm water from a thermos I'd filled before the power went out, and poured it over the foil. Within a minute, the jar was warm to the touch. Within 5 minutes, it was too hot to hold comfortably. I wrapped it in a towel and set it between my feet under a blanket. It held noticeable warmth for over 30 minutes. I repeated it 3 times through the night with fresh foil each time. It was not a furnace. It was not a replacement for a heating system, but it was real warmth from real chemistry, using materials I already had when nothing else was available and the temperature was still falling. Here is the one thing people get wrong when they first try this. They use flat sheets instead of crumpled foil. A flat sheet has minimal surface area exposed to the salt water. The reaction crawls, they feel barely any heat, and assume the whole concept is fake. Crumple the foil loosely. Tear it into irregular strips. You want maximum contact between the aluminum surface and the salt solution. More surface area means more simultaneous reaction sites, which means faster heat generation and higher peak temperatures. The difference between a flat sheet and a loosely crumpled ball in the same jar of salt water is the difference between a lukewarm cup and a jar you cannot grip barehanded. Now, here is the honest limitation, and it matters. This reaction is not perpetual. It is not free heat forever in the literal sense. The aluminum is consumed. Once it reacts, it becomes aluminum hydroxide, a chalky white residite with no remaining energy to give. A full roll of foil gives you roughly 45 minutes to an hour of meaningful heat output across multiple batches. The hydrogen gas produced is flammable. In a sealed container, it can build pressure. In an enclosed space without ventilation, it can reach concentrations that ignite from a spark. This is not theoretical. This is the exact reason fire marshals and legislators have taken notice. Used responsibly, in an open container in a ventilated space, as an emergency heat source when no other option exists, the reaction is manageable and genuinely useful. Used carelessly in a sealed room with an open flame nearby, it becomes dangerous. That distinction matters, and pretending it does not would be dishonest. But here is what also matters. The reaction itself cannot be patented. Patent examiners have reviewed aluminum salt heating devices repeatedly over the past 2 decades. Every filing runs into the same wall. The chemistry is prior art. It appears in freshman corrosion textbooks published 50 years ago. The ingredients are uncontrolled household commodities. No company can own the rights to a reaction between table salt and aluminum foil any more than they can patent the act of boiling water. The only patents that survive are for proprietary containers or packaging systems, not for the heat, not for the chemistry, not for the reaction you can reproduce in your kitchen in 30 seconds. And that is the problem. Not for you, for them. The North American propane industry alone generates over $35 billion in annual revenue. Natural gas heating adds another $80 billion. Hand warmer products, the commercial kind that use iron powder oxidation in a sealed packet, represent a $900 million global market. Every single one of those products delivers heat through a chemical reaction. Iron oxidation, combustion, catalytic conversion. All of them are packaged, branded, marked up, and sold back to you at margins that make the raw chemistry unrecognizable. A box of 10 commercial hand warmers costs $8 to $12. The iron powder inside each one costs less than 4 cents. You were paying for the packet, the branding, and the permission. The salt and foil reaction sidesteps all of it. No brand, no packet, no permission needed. And that is precisely why 23 states have now passed or adopted statutes, fire codes, or municipal ordinances that restrict, regulate, or outright prohibit unapproved chemical heating devices that generate heat through metal halide salt reactions. The language never says salt and aluminum foil. It says unapproved exothermic metal fuel devices. It says chemical heating apparatus not bearing UL certification. It says unauthorized hydrogen-generating heat sources. The words are different, the target is the same. This is not a new pattern. Every time a reaction too cheap to monetize proves too useful to ignore, the response follows the same sequence. First silence, then doubt, then regulation. Not because the chemistry is wrong, but because the economics are uncontrollable. You cannot meter salt. You cannot install a subscription on aluminum foil. You cannot send a monthly bill for a reaction that happens in a mason jar. And anything that cannot be billed has to be at minimum discouraged, at maximum outlawed. The chemistry has been sitting in plain sight for over a century. Every electrochemistry textbook published since the 1920s documents aluminum's reactivity with chloride solutions. Every corrosion engineer on the planet knows that salt destroys aluminum because it breaks the oxide barrier and exposes the raw metal to water. The reaction is not hidden, it is not classified. It's taught in university labs and demonstrated in high school science fairs. The only thing that changed is that people started asking a question nobody was supposed to ask. If this works in a lab, why not in my kitchen? If this works in my kitchen, why am I paying $400 a month to heat my house? The answer to that question is worth $115 billion a year to the people who would rather you never asked it. I don't know why you clicked on this video. Maybe the power went out last winter and you sat in the dark wondering what your options actually were. Maybe you're building an emergency kit and you want heat sources that don't depend on supply chains or refills. Maybe you just like understanding how things work at a level deeper than what the packaging tells you. It doesn't matter. The chemistry doesn't care about your reason. It works the same way in every jar, every garage, every freezing night when the grid goes down and the only thing between you and the cold is what you already have in the kitchen drawer. $4 of materials, 30 seconds to start. Real, measurable heat from a reaction that has been documented for 100 years, exposed right here and available to you right now. Take care of yourself, and I'll see you in the next one.